engineering underpins everything humans build and use. It transforms concepts into structures, machines, and systems that shape our environment and propel civilization forward. This series explores the 100 most important engineering ideas, core principles, and innovations that have defined and continue to drive the discipline. At the heart of engineering lies the understanding of forces and equilibrium, governing how bodies respond to loads and enabling safe, functional design of structures and machines. Newton's laws provide the framework for analyzing motion and static balance, essential for everything from bridges to rockets. Vector resolution of forces allows engineers to simplify complex loadings into manageable components. Stress and strain reveal how materials deform and fail under loading. The relationship defined by Hooke's law and material-specific properties guides the selection and application of metals, polymers, composites, and concrete to ensure structural integrity and longevity. Material behavior under tension, compression, shear, and torsion informs every engineering decision. Understanding moments and bending allows prediction of deflections and stresses within beams and structural elements subjected to off-center loads. Calculating bending moments and shear forces ensures that structural components can safely carry applied loads without excessive deformation or failure. Dynamics and vibrations address how structures and machines respond to time-varying forces, enabling prediction and mitigation of resonance, fatigue, and instability. Mathematical modeling of dynamic systems enables design for longevity and comfort in bridges, machinery, and vehicle suspensions. Thermodynamics governs energy transfer and conversion within engines, refrigerators, power plants, and chemical processes. The conservation of energy and principles like entropy define efficiency limits and fuel the development of sustainable technologies. Fluid mechanics describes the behavior of liquids and gases fundamental to aerospace, hydraulics, and process engineering. Continuity, Bernoulli's principle, and Navier-Stokes equations form the basis for pump and turbine design, weather forecasting, and biomedical devices. Materials science uncovers the microstructure mechanical property relationships vital to selecting or innovating materials tailored for specific engineering requirements. This knowledge informs everything from nanoscale electronics to massive concrete dams. Manufacturing processes are the practical means by which raw materials become complex components. Understanding casting, machining, welding, and additive manufacturing ensures quality production aligned with design intent. Control systems keep machines and processes operating safely and efficiently, from thermostats to autopilots. Feedback control ensures stability and performance within dynamic environments. Electrical engineering and circuit theory are the foundation of digital technology and power systems, governing current, voltage, resistance, and signal processing, enabling modern communications and computing. Architectural engineering blends structural integrity with functionality and aesthetics to create livable, resilient buildings, integrated with their environment. Project management and systems thinking ensure that complex engineering endeavors meet scope, schedule, and budget goals through planning, risk mitigation, and stakeholder coordination. Computation and simulation empower engineers to analyze complex phenomena and optimize designs, accelerating innovation cycles and enhancing reliability. Together, these ideas knit a rich tapestry, forming engineering's core. Mastery of their principles opens doors to understanding the technological world and pushing its boundaries further. Energy lies at the foundation of engineering, driving every machine, process, and infrastructure that powers civilization. Grasping the principles governing energy transformation, conservation, and degradation is essential to designing efficient, reliable, and sustainable systems capable of meeting diverse human needs. This part explores the fundamental concepts and applications of energy in engineering, comprising thermodynamics, fluid power, electrical energy systems, and emerging technologies redefining our capability to harness and utilize energy. At the core is the law of conservation of energy, often referred to as the first law of thermodynamics. It declares energy cannot be created or destroyed, but only converted from one form to another. This fundamental truth enables engineers to account for all energy entering, leaving, or stored within systems, empowering quantitative analysis, design optimization, and performance predictions. Whether in a simple lever converting mechanical work or a complex power plant transmuting heat into electricity, accurate energy accounting is non-negotiable. Complementing this is the second law of thermodynamics, introducing the concept of entropy, a measure of energy dispersion and system irreversibility. This law reveals that real-world energy transformations are inevitably accompanied by losses through heat dissipation, friction, and inefficiencies. Recognizing these limitations spurred centuries of innovation in thermodynamics cycles. Carnot, Rankine, Brayton, and refrigeration cycles, detailing idealized, best-case scenarios against which engineers measure actual system performance. Such knowledge guides the development of heat engines, turbines, compressors, and air conditioning systems, maximizing output while minimizing waste. Fluid systems harness energy by exploiting fluid motion and pressure differentials. The principle of fluid mechanics governs the behavior of liquids and gases in motion and at rest. Continuity equation ensures mass conservation. Bernoulli's equation links pressure, velocity, and elevation. Navier-Stokes equations describe intricate flow patterns fundamental for pump, turbine, and aerodynamic designs. Engineers apply these principles in diverse domains, designing efficient piping for water treatment plants, optimizing airflow in HVAC systems, creating aerodynamic profiles for aircraft and automobiles, and enhancing fuel injection in combustion engines. In electrical energy transformation, electromagnetic principles underlie generators, transformers, motors, and power grids. Faraday's law of induction quantifies how varying magnetic fields induce electrical currents, forming the basis of ubiquitous energy conversion systems. Coupled with Ohm's law, these laws govern circuit performance, resistance losses, and power utilization. Advances in semiconductor physics enable discrete devices controlling current and voltage, facilitating complex logic circuits forming the backbone of digital electronics. Energy storage technologies address the intermittent nature of renewable sources and grid demands. Electrochemical storage, exemplified by lithium-ion batteries, involves intricate material science engineering, crafting electrode chemistry, electrolyte stability, and thermal management balancing energy density, safety, and cycle life. Mechanical storages such as pumped hydroelectric systems and compressed air storage convert electrical energy to potential forms, releasing it flexibly back to the grid on demand. Emerging technologies supercapacitors, flow batteries, hydrogen fuel cells expand options, enriching energy portfolios, supporting resilience and decarbonization goals. Understanding energy efficiency and exergy analysis equips engineers with tools to identify how much useful work can be extracted from energy sources and where improvements are feasible. These assessments inform system design decisions, material choices, and operational strategies, accelerating transitions towards sustainability. Heat transfer fundamentals embrace conduction, the microscopic exchange of thermal energy through materials, convection, the fluid-driven energy transport, and radiation, the electromagnetic emission of heat, enabling thermal management in engines, electronic devices, and building envelopes. Engineers exploit these mechanisms designing heat exchangers, insulation systems, and cooling technologies essential across industries. Modern renewable energy technologies, wind turbines, photovoltaic cells, tidal generators integrate energy principles with novel material applications and power electronics controlling variable outputs, assuring grid stability and reliability. Aerodynamics, photonics, and control systems collaborate, converging on optimized designs, scaling from small distributed systems to massive utility-scale installations. System integration challenges arise as distributed energy resources. Microgrids and smart grids demand dynamic, bidirectional energy flows, managed by AI-enabled control platforms, optimizing efficiency, demand response, and fault tolerance. Technological trends explore energy harvesting from ambient vibrations, thermal gradients, and electromagnetic fields powering IoT devices and enabling new classes of autonomous sensors and wearable electronics, extending operational longevity and functionality. Computational modeling and simulation employing finite element and computational fluid dynamics enable detailed energy flow visualization and efficiency optimization, supporting design innovations. In essence, the mastery of energy principles equips engineers with universal tools to design, analyze, and innovate systems essential for modern life, industrial growth, and environmental stewardship. These ideas form an indispensable core empowering humanity's continual pursuit of sustainable power solutions, illuminating all engineered endeavors. Material science is the backbone of engineering, shaping everything built, manufactured, and designed. Without understanding how materials behave, degrade, and interact, engineering would be little more than guesswork. This section dives deep into how the intrinsic properties of materials, from atomic structures to macroscopic traits, influence performance, selection, and innovation across all engineering disciplines. At the atomic level, materials are defined by their crystal structures, which determine mechanical, thermal, and electrical behaviors. Common structures like body-centered cubic BCC, face-centered cubic FCC, and hexagonal close-packed HCP arrangements create distinct slip systems dictating how materials deform under stress. Dislocations, line defects, and crystal lattices govern plastic deformation, allowing metals to bend without breaking. Understanding these microscopic mechanisms empowers engineers to predict yield strength, toughness, and ductility, critical for safe, optimized designs. Materials broadly classify into metals, ceramics, polymers, composites, and emerging nano-engineered materials, each bringing unique advantages and limitations. Metals usually exhibit high strength and ductility, making them suitable for load-bearing applications. Ceramics provide excellent hardness and heat resistance, but are brittle, restricting their use under tensile stress. Polymers feature versatility and corrosion resistance, but often lack mechanical strength. Composites combine multiple materials, synergizing properties to outperform single material counterparts. Illustrated by carbon fiber reinforced polymers, revolutionizing aerospace and automotive industries. Phase diagrams map temperature and composition relationships, revealing phase stability, crucial in alloy design and heat treatment processes. Engineers manipulate these phases to achieve desired microstructures, balancing hardness, toughness, and malleability. For example, controlling cooling rates to form martensite in steels, enhancing hardness or tempered perlite for toughness. Thermal properties, conductivity, expansion coefficients, specific heat, govern material response to temperature changes, informing design decisions from turbine blades facing extreme heat to bridges experiencing daily thermal cycles. Engineers must balance these with operational conditions to prevent catastrophic failures such as thermal fatigue or buckling. Electrical properties vary widely, defining materials as conductors, semiconductors, or insulators. Advances in semiconductor physics paved the way for modern electronics, utilizing bandgap engineering to tailor electrical conductivity, enabling transistors, diodes, and integrated circuits, foundational to computers and communication systems. Corrosion and degradation mechanisms represent pervasive challenges. Electrochemical corrosion, wear abrasion, fatigue cracking, and environmental factors degrade materials over time. Protective measures, coatings, cathodic protection, material selection, extend service life, and ensure safety, particularly in infrastructure exposed to harsh environments such as marine or industrial settings. Materials processing techniques significantly influence final performance. Casting, forging, extrusion, rolling, and additive manufacturing introduce microstructural changes impacting grain size, residual stresses, and defect distributions. Precise control over processing parameters enables property tuning, such as grain refinement for enhanced strength or directional solidification, improving creep resistance. Recent progress in nano and bio-inspired materials opens new frontiers. Nanomaterials exhibit exceptional mechanical strength, electrical properties, and chemical reactivity derived from size effects and surface phenomena. Graphene's remarkable conductivity and strength exemplify this potential. Biomimicry inspires design of materials mimicking natural resilience and adaptability. Self-healing polymers, hierarchical composites offering unprecedented durability and multifunctionality. Sustainability is increasingly integral in materials engineering. Life cycle assessments evaluate environmental impacts from extraction, processing, use, and disposal, driving development of green materials, biodegradable polymers, recycled metals, low-carbon concretes, reducing ecological footprints. Circular economy principles promote material recovery, reuse, and recycling combined with design for disassembly supporting resource efficiency. Multi-scale modeling links atomic scale phenomena with macroscopic behavior, using computational methods such as molecular dynamics, finite element analysis, and phase field modeling, enabling virtual experiments and material design acceleration, reducing costly physical prototyping. Materials characterization employs diverse techniques. X-ray diffraction reveals crystal structures. Electron microscopy visualizes microstructures and defects. Spectroscopy analyzes composition. Mechanical testing quantifies strength, toughness, and hardness, providing critical feedback to validate and optimize materials for application-specific requirements. An intimate understanding of materials empowers engineers to push boundaries, creating lighter, stronger, more durable, and environmentally responsible infrastructures and technologies. This mastery enables innovation from skyscrapers withstanding earthquakes to flexible electronics revolutionizing communication. By weaving science with creativity, material science fuels engineering's perpetual quest to transform resources into the scaffolds of progress, continuously redefining what is possible. Structural mechanics forms the cornerstone of engineering, transforming abstract forces and motions into concrete understandings that ensure buildings stand. Bridges hold traffic and machines operate reliably. It bridges the realms of applied physics and mathematics to predict how structures respond under loading, enabling the design of safe, efficient, and resilient systems. This part unfolds the key principles and analytical tools essential to structural behavior, introducing engineers to the complex interplay of forces, stresses, deformations, and stability. Fundamentally, structures must maintain equilibrium, meaning all forces and moments acting upon them balance to prevent uncontrolled motion or collapse. Engineers analyze these conditions by isolating structural elements and applying Newton's laws to establish static or dynamic force balance equations. This systematic approach forms the basis of structural analysis, checking whether components carry their intended load safely and predicting responses to external influences from gravity and wind loads to seismic events. Stress and strain continue their canvas, but now viewed within complex structural forms. Normal stress arises from axial loading, causing elongation or compression, whereas shear stress results from transverse forces inducing sliding deformations. Torque induces torsional stress, critical in rotating shafts, while bending forces create complex flexural stresses, varying through cross-section depths. Understanding these stress distributions allows assessment of whether materials remain within safe limits or risk plastic deformation and failure. Key to bending analysis is the moment-curvature relationship, linking bending moments to curvature through material and geometric properties. The section modulus and moment of inertia quantify a member's capacity to resist bending and deflection, enabling optimizations balancing strength and material economy. For example, I-shaped steel beams achieve high bending resistance with minimal weight, a result of strategically placing material far from the neutral axis to maximize moment of inertia. Shear force diagrams, SFD, and bending moment diagrams, BMD, graphically represent internal forces and moments varying along beam lengths, providing intuitive visualization complemented by precise calculation. These diagrams identify critical points requiring reinforcement or design modification, essential in civil, mechanical, and aerospace structures. Beyond linear elasticity, many structures require assessment of buckling and stability, where compressive forces can precipitate sudden failure well before material yield strength is reached. Euler's buckling formula calculates critical load thresholds for slender columns, informing their design to avoid catastrophic collapse by selection of appropriate cross-sectional geometry, length, and boundary conditions. Dynamic structural analysis delves into behavior under vibration and impact loading. Natural frequencies, mode shapes, and damping characteristics dictate a structure's response to seismic forces, wind-induced oscillations, or machinery vibrations. Employing modal analysis enables engineers to ensure that operating frequencies avoid resonance that could amplify deformations and cause fatigue failure. Innovative solutions like tuned mass dampers installed atop skyscrapers mitigate sway-enhancing occupant comfort and long-term durability. The concept of plasticity and fracture mechanics examines material response beyond elastic limits, predicting when localized yielding or crack propagation becomes critical. The yield criterion, e.g. von Mises-Tresca, defines the onset of plastic flow under combined stresses guiding design against permanent deformation. Fracture toughness evaluates a material's resistance to crack growth, providing reliability assessments, crucial in aerospace and pressure vessel engineering. Modern analysis employs finite element methods, FM, discretizing complex structures into small elements over which governing equations are balanced numerically. FM enables modeling of irregular geometries, anisotropic materials, and nonlinear behaviors unmanageable by classical analytical approaches. It empowers engineers to simulate real-world conditions with high-fidelity predicting stresses, displacements, and failure modes, ensuring optimized designs before physical prototyping. Understanding load paths through structures reveals how forces transfer from external application points to foundations. Well-conceived load paths prevent unintended stress concentrations, distribute demands efficiently, and promote redundancy, critical for structural safety under unforeseen damages or overloads. Material heterogeneity and anisotropy introduce additional complexities. Composite materials, layered laminates, or reinforced concrete exhibit direction-dependent properties requiring advanced constitutive models and tailored analytical techniques to capture real behavior, ensuring accurate design margins. Integration of soil structure interaction characterizes how foundations and soil respond together under load. Detailed geotechnical analyses assess settlement, bearing capacity, and lateral earth pressures informing pile design, mat foundations, and retaining walls. adapting structural solutions to ground realities. Sustainability considerations influence structural engineering choices, emphasizing material efficiency, life cycle impacts, adaptability to changing loads and climates, and ease of maintenance and eventual deconstruction. Innovative materials, like ultra-high performance concrete and corrosion-resistant alloys, extend service lives, reducing environmental and economic costs. In infrastructure exposed to seismic hazards, performance-based design evaluates structural behavior under realistically simulated earthquake loads, enabling engineers to design structures that not only survive but remain functional, minimizing economic disruption and loss of life. In summary, structural mechanics is a multi-dimensional science blending physics, materials, and mathematics, essential to translating abstract loads into tangible, safe, and efficient forms. Mastery over these principles empowers engineers to elevate architecture, transport, energy, and industrial systems into enduring landmarks of human ingenuity and reliability. Fluid mechanics and thermodynamics form the twin pillars underlying countless engineering systems, from the propulsion systems of aircraft and automobiles to the heating, ventilation, and air conditioning (HVAC) in buildings and the energy conversion processes powering cities. Mastering their principles enables engineers to manipulate fluids and energy in ways that maximize efficiency, reliability, and sustainability across diverse applications. This section presents an in-depth exploration of the essential ideas shaping fluid and thermal engineering. Fluid mechanics describes the behavior of fluids, both liquids and gases, in motion and at rest. Its foundation lies in the fundamental laws of conservation: mass, momentum, and energy. The continuity equation expresses mass conservation, stating that the mass flow rate through any cross-section of a steady system remains constant. This principle ensures that fluids neither accumulate nor disappear as they flow, forming a baseline for analyzing piping systems, ductwork, and blood flow. The Navier-Stokes equations govern fluid dynamics by relating forces due to pressure, viscous stresses, and body forces to fluid motion. These nonlinear partial differential equations capture complex behaviors including laminar and turbulent flow, boundary layers, vortex formation, and wake effects. Given their mathematical complexity, numerical methods, and computational fluid dynamics, CFD simulations are employed extensively to model real-world fluid phenomena accurately. The Bernoulli equation simplifies fluid flow analysis under assumptions of incompressibility and non-viscous flow, relating pressure, velocity, and elevation. It serves to design efficient pumps, turbines, wind tunnels, and airplane wings, where pressure differences generate lift or enable energy recovery. Distinguishing laminar from turbulent flow is essential. Laminar flow features smooth, orderly layers with predictable velocity profiles, dominating at low velocities or high viscosities. Turbulent flow involves chaotic fluctuations and mixing, increasing drag and energy loss but enhancing heat and mass transfer, crucial in reactors and heat exchangers. Reynolds number quantifies the flow regime, guiding design and control strategies. Fluid properties such as viscosity, density, compressibility, and surface tension influence flow behavior and system performance. The viscosity defines internal friction resisting motion, critical for pump selection and lubrication design. Compressibility becomes significant in high-speed gas flows, affecting shock wave formation in supersonic aircraft and pressure vessel design. Surface tension governs droplet formation and capillary action relevant in microfluidics and coating technologies. Thermodynamics governs energy transformations, conducted via heat and work, illuminating how engines, refrigerators, and power plants convert fuel or ambient energy into useful work or temperature control. The first law of thermodynamics formalizes energy conservation at system boundaries, balancing heat, work, and internal energy change, providing a universal accounting framework for energy analysis. The second law of thermodynamics introduces entropy and dictates the direction of spontaneous processes, emphasizing that energy conversions are never completely efficient. This reality compels engineers to design systems approaching optimal efficiency via optimized cycle selection, component design, and waste heat recovery. Reversible processes serve as idealized benchmarks, guiding real-world improvement efforts. Common thermodynamic cycles include the Carnot cycle, representing the maximum theoretical efficiency, the Rankine cycle, governing steam power plants, the Brayton cycle, fundamental to gas turbines, and the refrigeration cycle, essential to cooling and heat pump technology. Engineers carefully select, combine, and adapt these cycles within systems to meet efficiency, environmental, and economic constraints. Heat transfer encompasses conduction, convection, and radiation, the mechanisms by which energy in the form of heat moves through solids, fluids, and across spaces. Conduction arises through molecular vibration and electron movement in solids, characterized by Fourier's law defining heat flux in response to temperature gradients. In fluids, convection integrates conduction with bulk movement, facilitating heat transport critical in HVAC engines and chemical reactors. Radiation involves electromagnetic waves transferring energy without requiring a medium, fundamental in solar energy harvesting and thermal insulation. In practical systems, heat exchangers exploit these mechanisms to transfer heat between fluids without mixing. Plate, shell and tube, and compact heat exchangers vary in configuration, balancing surface area, pressure drop, and thermal effectiveness tailored to applications ranging from power plants to refrigeration. Fluid power refers to hydraulic and pneumatic systems harnessing pressurized fluids to transmit energy efficiently. Hydraulic machinery delivers high force with precise control in heavy equipment, industrial presses, and aircraft controls. Pneumatics offers rapid actuation using compressed air in automation and manufacturing. Engineering these systems demands understanding fluid compressibility, flow control, sealing, and filtration to maintain responsiveness and avoid leaks or failures. Emergent fields such as microfluidics involve manipulating minute fluid volumes in channels smaller than a millimeter, enabling lab-on-chip technologies revolutionizing biomedical diagnostics, chemical synthesis, and environmental monitoring. These systems probe the interplay of fluid mechanics at small scales, including surface tension and laminar flow dominance. Environmental engineering benefits from fluid and thermal principles too. Managing river flows for flood control, designing efficient water treatment plants, modeling pollutant dispersion in air and water, and optimizing renewable energy capture from wind and solar thermal resources. Advances in numerical simulation, high-speed data acquisition, and experimental techniques accelerate understanding, allowing engineers to model transient phenomena and optimize designs in domains as diverse as combustion, aerodynamics, HVAC, and renewable energy systems. In essence, the mastery of fluid mechanics and thermodynamics equips engineers with the tools to control energy and matter flows fundamental to shaping the built and natural environments harmoniously and efficiently. Control systems and automation have revolutionized engineering, embedding intelligence and precision into processes, machines, and infrastructure worldwide. From thermostats regulating home temperatures to autonomous vehicles navigating city streets and industrial plants operating with minimal human oversight, control engineering underpins the modern technological landscape. This section delves into the foundational concepts, mathematical frameworks, and contemporary applications that make control systems indispensable to engineers. The essence of control systems lies in feedback, a mechanism where a system's output is measured and compared against a desired set point, with corrections applied to reduce errors. This dynamic adjustment enables systems to maintain stability and performance despite disturbances and uncertainties. The classical example is a home heating thermostat. It senses room temperature, compares it with the target, and modulates the heater to keep temperature steady. Mathematically, control systems are modeled as input-output relationships often expressed through differential equations, capturing system dynamics. Linear time invariant LTI systems serve as a cornerstone, enabling the use of transfer functions and Laplace transforms which simplify analysis and controller design. Engineers develop models that predict how systems respond to inputs and disturbances. Accuracy in these models is critical for robust control. Two primary control strategies are feedback and feed-forward control. While feedback reacts to discrepancies, feed-forward anticipates disturbances based on measurable inputs, allowing preemptive corrections, enhancing responsiveness. Combining both yields more sophisticated controllers capable of handling complex, nonlinear, and time-varying systems encountered in advanced applications. The PID controller, proportional, integral, derivative, remains the most widely used feedback algorithm due to its simplicity and effectiveness. The proportional term reacts proportionally to current errors. The integral accumulates past errors, eliminating steady-state offsets. The derivative predicts future errors, improving stability. Tuning these parameters correctly is a practical engineering art, balancing responsiveness with overshoot and oscillations. Modern control theory extends beyond classical methods, embracing state space representations which capture multi-input, multi-output systems in matrix form, permitting comprehensive analysis and control design, especially for complex aerospace, robotics, and process systems. Concepts like controllability and observability assess whether inputs can drive the state to desired conditions and whether internal states can be inferred from outputs respectively, critical for designing effective controllers and observers. Optimal control and model predictive control (MPC) represent state-of-the-art methodologies, incorporating system constraints and objectives, solving optimization problems in real time to achieve desired performance. MPC, for instance, predicts future system behavior over a finite horizon and optimizes control actions accordingly. Widely used in chemical processing, automotive, and energy sectors. Sensors and actuators form the physical interface for control systems. Precise measurement and signal conditioning capture real-world parameters: temperature, pressure, position, speed, with increasing accuracy. Enabled by developments in MEMS micro-electromechanical systems, optical sensors, and wireless telemetry. Actuators ranging from simple valves and motors to complex robotic arms and jet engines execute control commands directly affecting system behavior. The rise of digital control systems leverages microcontrollers, programmable logic controllers (PLCs), and industrial PCs, enabling flexible, reconfigurable, and networked control architectures integrated with SCADA, supervisory control, and data acquisition for wide area monitoring and control. Software frameworks incorporating real-time operating systems ensure deterministic timely execution, critical for safety and performance. Automation extends control principles to entire production lines and infrastructure through programmable automation controllers, coordinating robotic assembly, conveyor systems, logistics, and quality control, enhancing productivity while reducing human error and exposure to hazardous environments. Artificial intelligence and machine learning increasingly supplement traditional control by enabling systems to learn from experience, adapt to uncertain environments, and optimize performance beyond manually tuned controllers. Autonomous vehicles and smart grids exemplify AI-driven control, integrating sensor fusion, pattern recognition, and predictive algorithms. Safety-critical control systems incorporate redundant architecture, fault detection, and fail-safe protocols ensuring continuous operation, or safe shutdown in faults, vital in aerospace, nuclear, and medical applications. Rigorous verification and validation processes employing formal methods guarantee controller correctness, reducing risk. Human-machine interfaces. HMIs facilitate intuitive system monitoring and interaction through graphical displays, touch screens, and augmented reality, improving operator situational awareness and decision-making in complex environments. Embedded control systems within consumer electronics, medical devices, and transportation showcase the ubiquity and indispensability of control engineering in daily life, enhancing convenience, safety, and efficiency. Emerging trends include distributed control architectures supporting IoT-enabled industrial networks, cloud-based control for remote operations, and cyber-physical systems integrating sensing, computation, networking, and physical processes into cohesive, intelligent ecosystems. Control systems and automation synthesize mathematics, physics, electronics, and computer science into powerful tools, transforming raw engineering into smart, adaptive, and efficient technological realities. Mastery of these principles empowers engineers to design systems that not only function but thrive amid complexity and change. Electrical engineering and digital systems are the foundation stones of the modern technological era, powering everything from household devices to global communications networks, automation systems, and computational infrastructures. This part delves deeply into the core concepts of electricity, circuit theory, and digital logic that underpin the functionality and innovation seen in countless engineering applications. Electricity itself is a phenomenon arising from the movement and interaction of charged particles, primarily electrons in conductors. Voltage, the potential difference driving charge flow, combined with current, the rate of charge flow, form the fundamental electrical quantities. Their relationship with resistance, opposition to current governed by the material and geometry expressed by Ohm's law, defines the behavior of circuits. Engineers exploit these principles to design and analyze everything from simple flashlight circuits to complex power grids. Basic circuit components: resistors, capacitors, inductors, diodes, and transistors serve as the building blocks enabling signal control, energy storage, and conversion. Capacitors store electric charge and release it, enabling filtering and timing. Inductors store energy in magnetic fields, helpful in tuning and regulation. Diodes allow current flow in one direction, forming rectifiers, essential for converting AC to DC power. Transistors act as switches and amplifiers, the heart of modern electronics, enabling the creation of integrated circuits. The study of alternating current AC expands understanding beyond static DC behavior, introducing phenomena such as phase angle, reactance, impedance, and power factor essential for efficient power transmission and conversion. Engineers design transformers adjusting voltage levels, minimizing losses on long-distance power lines, creating the backbone of electrical distribution systems. Frequency standards ensure synchronization and stability, critical to operation in grids. Digital systems mark a revolution by representing information in discrete binary form, zeros and ones, which simplifies storage, transmission, redundancy, and processing. Boolean algebra governs digital logic, enabling the creation of gates and or not, which combine into networks realizing arithmetic, control, and decision-making functions. This abstraction leads to the design of complex digital circuits, comprising multiplexers, flip-flops, registers, and counters, forming memory and processing units. Microprocessors and microcontrollers integrate millions to billions of transistors, implementing arithmetic logic units, control units, and memory subsystems, enabling programmable control in countless applications from smartphones to household appliances and industrial automation. Von Neumann and Harvard architectures define crucial computational designs, optimizing data flow, instruction execution, and system performance. Analog to digital conversion and vice versa. Bridge the real analog world with the digital realm, allowing sensors measuring continuous physical quantities, temperature, pressure, light, to interface with digital control systems. Sampling theory, Nyquist frequency, and quantization error guide engineers in faithfully capturing and reconstructing signals, minimizing distortion or information loss. Signal processing, both analog and digital, extracts, filters, compresses, and analyzes information embedded in electrical signals, enabling applications in communications, imaging, speech recognition, and control. Fourier analysis decomposes signals into frequency components, revealing hidden structures, facilitating efficient data handling and noise reduction. Communications engineering builds upon these principles, transmitting information reliably across noisy channels, employing modulation schemes, amplitude, frequency, phase, coding theory for error detection and correction, and multiplexing, maximizing bandwidth efficiency. Wireless networking, fiber optic transmission, and satellite links form the global framework, enabling the internet, telephony, and media services fundamental to all modern activities. Electrical machines, including motors, generators, transformers, and power electronics, convert electrical energy into mechanical motion and vice versa, enabling industrial automation, electric transportation, and renewable energy integration. The design of efficient, reliable machines accounting for electromagnetic, thermal, and mechanical loads advances continuous performance improvements. Emerging fields like quantum computing, nanoelectronics, and flexible electronics push the boundaries of electrical engineering, unlocking new capabilities in speed, miniaturization, and integration, heralding future technology revolutions. Electrical safety considerations, grounding, isolation, circuit protection, ensure safe operation protecting personnel and equipment from hazards. Regulatory standards and international codes govern electrical designs, enforcing reliability and safety, essential for public trust. Power systems engineering manages generation, transmission, distribution, and consumption, orchestrating grid stability, demand response, and integration of distributed energy resources, enabled by smart grid technologies, incorporating real-time monitoring, adaptive control, and automated fault detection. Sustainability increasingly guides electrical engineering through energy-efficient device design, renewable energy systems. In totality, electrical engineering and digital systems form the nervous system of modern civilization, enabling information age technologies and controlling physical processes with unprecedented speed, precision, and versatility. Manufacturing processes and production engineering bridge the gap between conceptual design and tangible products, transforming raw materials into precisely crafted components and assemblies that serve as the backbone of modern technology and infrastructure. This part explores the myriad fabrication methods, their scientific principles, control methodologies, and strategic integration essential for achieving quality, efficiency, and scalability in engineering. The journey begins with casting and molding, fundamental methods for shaping materials by pouring molten substances into shaped cavities, allowing complex geometries impossible in machining alone. Sand casting, die casting, investment casting, and injection molding each address specific trade-offs between surface finish, dimensional accuracy, production volume, and material compatibility. Engineers meticulously control cooling rates and mold design to manage microstructure, minimize residual stresses, and avoid defects such as porosity or shrinkage. Casting remains indispensable in producing engine blocks, turbine components, and structural parts. Forming processes transform materials by plastic deformation without removing material. Techniques such as forging, rolling, extrusion, and sheet metal forming harness mechanical forces to refine grain structure, enhance strength through work hardening, and produce near-net shapes, reducing machining. Hot and cold working conditions alter material properties diversely. For example, hot forging enables significant deformation, mitigating cracking, while cold rolling improves surface finish and dimensional precision. Process parameters, strain rate, temperature, lubrication are optimized for material flow and minimizing defects like wrinkling or tearing. Machining processes, turning, milling, drilling, grinding, employ material removal to achieve tight tolerances and surface quality. Precision depends on tool geometry, feed rate, cutting speed, coolant application, and machine rigidity. Advancements such as CNC, computer numerical control, automate machining with programmable accuracy, enabling reproducibility and complex tool paths essential for aerospace, medical, and automotive components. Cutting tool materials. Coatings and wear monitoring significantly influence process economics and quality. The advent of additive manufacturing (AM) 3D printing has revolutionized fabrication paradigms by enabling layer-by-layer material deposition to create intricate geometries directly from digital models. Technologies include fused deposition modeling (FDM), selective laser melting (SLM), stereolithography (SLA), and electron beam melting (EBM, each suitable for distinct materials and applications. AM enables customization, reduces waste, accelerates prototyping, and fosters design innovation by circumventing traditional machining constraints. Challenges include surface finish, residual stress management, and process standardization, demanding multidisciplinary expertise. Joining techniques such as welding, brazing, soldering, and adhesive bonding assemble parts into functional systems. Welding involves local melting and fusion, creating strong, permanent joints. Process variants, arc, laser, friction stir, offer tailored heat input and material compatibility, balancing joint quality and distortion. Brazing and soldering utilize lower temperature filler metals for delicate assemblies, while adhesives provide load distribution advantages for composite structures. Successful joining requires understanding metallurgical transformations, thermal cycles, and residual stress impacts, ensuring durability and safety. Production engineering emphasizes process planning and optimization, selecting sequences and parameters, maximizing throughput, minimizing cost, and assuring quality. Value stream mapping identifies bottlenecks and waste, while just-in-time JT manufacturing synchronizes supply chains with production demands, reducing inventories and lead times. Lean manufacturing principles eliminate non-value-adding activities, improving process flow and worker engagement. Quality control integrates statistical process control, SPC, Six Sigma methodologies, and non-destructive testing, NDT tools, including ultrasonic, radiographic, magnetic particle inspections, detecting defects and assuring compliance with stringent specifications. Metrology systems utilizing coordinate measuring machines, laser trackers, and vision systems provide precise dimensional verification supporting continuous improvement. Automation in production lines employs robotics, automated guided vehicles, AGVs, and intelligent control systems, increasing consistency, speed, and safety. Collaborative robots, cobots, work alongside humans, augmenting flexibility in assembly tasks, requiring adaptability and precision. Sustainability in manufacturing drives innovation in energy-efficient processes, waste minimization, material recycling, and green chemistry adopting life cycle thinking and environmental management systems. ISO 14001 Circular economy principles promote design for disassembly, remanufacturing, and resource valorization, minimizing environmental impact. Emerging paradigms like Industry 4.0 integrate cyber-physical systems, Internet of Things, IoT, big data analytics, and artificial intelligence enabling smart factories capable of self-optimization, real-time decision-making, and adaptive maintenance revolutionizing productivity and resilience. Globalization and supply chain complexity introduce considerations around logistics, risk management, and compliance with international standards, ensuring timely and quality delivery amidst geopolitical and market fluctuations. In conclusion, manufacturing and production engineering represent a sophisticated interplay of material science, mechanical technology, management science, and digital innovation. Mastery of these processes empowers engineers to realize design intent with unmatched precision, scalability, and sustainability, forming the physical foundation of all engineered products, shaping modern life. Construction engineering and infrastructure development stand as monumental endeavors at the intersection of design ingenuity, materials mastery, and logistical orchestration, transforming blueprints into the physical frameworks upon which societies thrive. This domain encompasses the planning, management, execution, and maintenance of large-scale projects such as highways, bridges, tunnels, airports, water and power networks, and urban developments that collectively form the backbone of modern civilization. At the outset lies project planning and scheduling, a foundational discipline coordinating thousands of concurrent activities within stringent time, cost, and resource constraints. Techniques like the critical path method, CPM, and program evaluation and review technique model dependencies optimizing sequences, enabling dynamic adjustments to mitigate delays. Resource leveling balances labor, equipment, and material availability, preventing bottlenecks, ensuring smooth workflow progression, even amid uncertainties inherent in megaprojects. Site investigation and geotechnical analysis critically inform foundation designs, ensuring stability and safety in diverse soil and rock conditions. Techniques including borehole drilling, standard penetration testing, and geophysical surveys characterize subsurface profiles identifying load-bearing strata, groundwater tables, and potential hazards like liquefaction or settlement. These data guide optimal foundation choices, spread footings, deep piles, grouted anchors, tailored to structural demands and environmental factors. Construction methodologies vary from traditional cast-in-place concrete and masonry to advanced precasting and modular fabrication, enabling accelerated schedules, enhanced quality control, and waste reduction. Innovations including tunnel boring machines, TBMs equipped with precision guidance systems, facilitate underground excavations beneath dense urban and geological constraints, minimizing surface disruptions, crucial for metros and utilities. Expansion. Temporary work such as scaffolding, false work, cofferdams, and earth retention systems support safe and effective construction operations accommodating loads, movements, and climate variations. Engineering these structures demands detailed analysis of stability, load pathways, and interaction with permanent elements, ensuring worker safety and structural integrity throughout construction phases. Building information modeling. BIM extends into construction management, enabling virtual construction sequencing, 4D BIM, visualizing spatial and temporal progress, facilitating early conflict detection, material logistics planning, and stakeholder communication, enhancing decision-making, and reducing rework. Quality assurance in construction incorporates rigorous inspection regimes covering material properties, workmanship, and adherence to specifications. Non-destructive testing, NDT methods such as ultrasonic pulse velocity, rebound hammer, and infrared thermography detect subsurface defects, ensuring structural performance and durability without impairing integrity. Health, safety, and environmental management permeate construction, embedding proactive hazard identification, safety training, stray force protection, and environmental control, mitigating dust, noise, and ecological impacts, aligning with regulatory frameworks and community expectations, fostering social license. Massive infrastructure projects navigate complex stakeholder landscapes involving governments, private sector, communities, and environmental groups, necessitating transparent governance mechanisms, participatory planning, and dispute resolution, fostering equitable benefits and minimizing conflicts. Sustainability in construction embraces selection of green materials, energy-efficient construction techniques, waste minimization, and ecosystem preservation, integrating circular economy principles and carbon footprint assessments throughout project life cycles, advancing environmentally responsible infrastructure. Advanced construction technologies integrate robotics, automating repetitive or hazardous tasks, enhancing productivity and safety. Drones provide aerial monitoring and progress documentation, augmented and virtual reality, foster immersive training, design validation, and real-time issue resolution, bridging spatial and knowledge gaps. Logistics and supply chain engineering ensure timely quality delivery of vast material quantities, coordinating multimodal transportation, storage, and just-in-time deployment, adapting dynamically to site constraints and external disruptions, minimizing downtime and cost overruns. Post-construction activities, including commissioning, maintenance planning, and asset management, employ sensor networks and digital twins, enabling condition monitoring, predictive maintenance, and life cycle optimization, maximizing infrastructure availability and value. In essence, construction engineering is a grand choreography of science, technology, management, and craftsmanship, converting visionary designs into tangible, enduring infrastructures, fundamentally supporting societal advancement, economic vitality, and quality of life. Transportation engineering and mobility systems form the lifeblood of modern civilization, enabling the movement of people, goods, and information across ever-expanding networks that connect cities, regions, and countries. This domain combines civil, mechanical, electrical, and increasingly digital engineering principles to design, optimize, and operate infrastructures and vehicles, facilitating safe, efficient, sustainable transportation on land, water, and air. At the core lies traffic flow theory, which models how vehicles or pedestrians interact within transportation networks. Fundamental variables such as flow rate, density, and speed govern the macroscopic behavior of traffic streams. Engineers employ models ranging from simple green shields, linear relations, to complex cellular automata and fluid dynamic analogies to predict congestion, travel times, and system capacity, informing design and control strategies. Understanding shock waves, queue dynamics, and bottleneck phenomena enables proactive traffic management, improving throughput, and reducing delays. Highway and roadway design integrate geometric design principles, harmonizing cross-section dimensions, curvature, sight distances, grades, and super elevation to ensure safety and comfort at desired speeds. Pavement engineering incorporates material science and structural mechanics, optimizing layer composition, thickness, and surface properties, mitigating wear, rutting, and skid resistance over vehicle lifetimes. Intelligent road infrastructure employs embedded sensors and communication devices, facilitating adaptive lighting, hazard detection, and real-time traffic updates, enhancing user safety and experience. Railway systems blend precise civil engineering of tracks, subgrades, and signaling with mechanical engineering of rolling stock. Track alignment, ballast selection, and rail welding address dynamic loads and vibrations, maximizing ride quality and durability. Signaling systems evolve from traditional block signaling to advanced automatic train control and communication-based train control (CBTC). increasing capacity and operational safety. Recent innovations include magnetic levitation, maglev and hyperloop concepts promising ultra-high-speed, low-friction transport. Air transportation encompasses aerodynamic design, propulsion, navigation, and airport infrastructure. Aerodynamics governs lift, drag, and stability, shaping wing profiles, control surfaces, and fuselage to achieve efficient, controllable flight. Propulsion principles underpin jet engines and propellers, converting fuel energy into thrust with continuous improvements in thermal efficiency and emissions reduction. Air traffic management leverages radar, satellite navigation, and digital communication, ensuring safe, orderly flows in increasingly crowded skies. Airports integrate terminal design, runway layout, ground handling, and security systems, optimizing throughput and passenger experience. Urban transportation integrates multimodal networks composed of buses, trams, metros, bicycles, and pedestrian pathways. Effective planning must simultaneously handle land use interactions, service demand, equity, environmental impacts, and emerging micro-mobility trends. Transit-oriented development. TOD clusters high-density living near transit hubs, fostering sustainable, transit-efficient urban form, reducing reliance on private vehicles, curbing congestion and emissions. Maritime transportation involves ship design, targeting hydrodynamic efficiency, cargo capacity, and navigational safety. Ports incorporate complex logistics engineering, managing container, stacking, vessel berthing, intermodal transfer, and customs flows, accelerating global trade velocity. Environmental concerns prompt development of low-emission fuels, ballast water treatment, and hull coatings, reducing ecological footprints. Recent transformational technologies include autonomous vehicles employing sensor fusion, computer vision, artificial intelligence, and communication, enabling self-driving cars, drones, and ships, promising enhanced safety, efficiency, and accessibility. Connected vehicle technology coordinates interactions among vehicles and infrastructure, forming the Internet of Transportation (IoT), optimizing traffic flow and incident response. Electric propulsion revolutionizes transportation, reducing greenhouse gas emissions and pollutant levels. Challenges in battery capacity, charging infrastructure, and life cycle sustainability continue to drive research and deployment strategies, particularly in urban transit and freight sectors. Transportation safety engineering employs human factors analysis, crashworthiness design, and resilient infrastructure planning, minimizing accident risks and mitigating injury severity through roadside barriers, rumble strips, automated enforcement, and emergency response integration. Optimization and simulation tools enable complex network analyses, balancing capacity, reliability, cost efficiency, and environmental impact, supporting strategic investments and real-time operational decisions. Multi-criteria decision analysis, MCDA, and agent-based modeling accommodate stakeholder preferences and emergent behavior, refining policy and project selection. Public policy, regulatory frameworks, and international conventions shape interface harmonization, standardization, funding mechanisms, and innovation diffusion guiding. Transportation system evolution aligned with societal goals around accessibility, equity, and sustainability. In conclusion, transportation engineering orchestrates an intricate symphony of infrastructure, vehicles, control systems, and policy interfacing to move societies forward, enhancing connectivity, economic vitality, and quality of life on a global scale. Energy systems engineering represents a vast multidisciplinary field, essential to sustaining modern society's expansive and growing demands. It encompasses the generation, conversion, transmission, distribution, storage, and management of energy resources derived from traditional and renewable origins. This segment delves deeply into the engineered systems conceived for efficient, reliable, and increasingly sustainable energy supply aligned with global climate, economic, and technological transformations. The cornerstone concept is energy conversion, the process of transforming raw energy forms into usable power. Thermal power plants convert chemical potential energy in fossil fuels or biomass into electricity through steam cycles, utilizing boilers, turbines, and generators. Understanding thermodynamic cycles. Rankine for steam, Brayton for gas turbines, and combined cycles integrating both enables efficiency optimization by maximizing work output and minimizing irreversible losses. Engineers carefully design heat exchangers, combustion systems, and condensers, orchestrating transfer mechanisms and fluid flows to elevate plant performance while mitigating pollutant emissions. Nuclear power introduces the complex interplay of nuclear physics and thermal hydraulics. It harnesses energy released from controlled fission reactions, producing immense heat driving steam turbines. Reactor designs pressurized water, boiling water, fast breeder, incorporate engineered safety systems, ensuring containment, decay, heat removal, and neutron moderation essential to safe continuous operation. Radiation shielding, fuel cycle management, and waste disposal embody critical engineering challenges, integrating material science, mechanical systems, and environmental safeguards. Renewable energy systems harness abundant, naturally replenishing sources transforming global energy paradigm. Solar photovoltaic PV systems convert sunlight directly into electricity via semiconductor junctions, with continuous research enhancing cell efficiency, spectral response, and manufacturing scalability. Concentrated solar power CSP plants employ mirrors and lenses focusing heat to drive turbines. Engineering challenges include material durability under intense radiation, thermal storage integration, and grid interface management. Wind energy systems convert aerodynamic forces on blades into mechanical rotation driving generators. Blade aerodynamics, structural dynamics, and control engineering synchronize to extract maximum power at varying wind speeds while ensuring reliability under extreme weather. Offshore wind farms require specialized foundation design dealing with marine conditions and fatigue loading. Hydropower converts gravitational potential energy of flowing or stored water into electricity. Dam design, hydraulic turbine selection. Pelton, Francis, Kaplan, and water conveyance engineering are vital to optimizing energy capture, while balancing ecological and social impacts. Emerging technologies include tidal and wave energy converters, exploiting ocean dynamics. Energy storage addresses the intermittent nature of many renewable sources, stabilizing supply. Battery technologies including lithium-ion, flow batteries, and emerging solid-state concepts balance energy density, cycle life, cost, and safety. Mechanical storages such as pumped hydropower and flywheels provide grid-scale balancing capabilities. Power-to-X technologies transform excess electricity into hydrogen, synthetic fuels, or chemicals, enabling sector coupling and carbon-neutral fuel production. Electric power transmission employs high-voltage AC and DC lines, minimizing losses over long distances. High-voltage direct current HVDC links enhance interregional grid connectivity, enabling renewable integration and energy trading. Grid stability encompasses advanced protections and control schemes managing frequency, voltage, and fault isolation, ensuring continuous, reliable service. Smart grid technologies embed sensing, communication, and computation throughout power networks, enabling real-time demand response, fault diagnosis, distributed generation coordination, and consumer engagement, fostering energy efficiency and resilience. Internet of Energy (IoE) concepts expand this paradigm, integrating electric vehicles, prosumers, and microgrids into cohesive ecosystems. Thermal energy systems cover district heating and cooling, combined heat and power plants, geothermal, and biomass technologies, providing reliable local energy solutions with reduced footprints. Heat pump engineering elevates waste or ambient heat to useful temperatures, improving building energy efficiency. Energy policy, economics, and environmental considerations profoundly impact system design and deployment. Life-scale assessments, carbon pricing, subsidies, and regulatory frameworks incentivize cleaner technologies, aligning engineering with sustainability goals. Societal acceptance and justice around resource access, land use, and transition impacts require integrative multidisciplinary approaches. Emerging domains include fusion energy research promising near-limitless clean power with engineering challenges of plasma confinement, materials resistance to neutron fluxes, and safe tritium handling. Advanced energy harvesting and nanotechnology enhanced energy materials increasing conversion efficiencies. Computationally, modeling multi-scale phenomena from nano-level electronic transitions in PV cells to macro-scale grid dynamics enables virtual prototyping, optimization, and scenario planning, reducing costs and accelerating innovation. Harnessing energy skillfully reflects humanity's prowess to manipulate fundamental forces, balancing constraints of physics, economics, environment, and society, delivering the power-sustaining contemporary civilization, and enabling future progress. Environmental engineering and water resources management represent critical fields dedicated to safeguarding the natural environment, ensuring clean water availability, and sustaining ecosystems amid accelerating human activity and climate change. Engineering solutions in these domains integrate chemistry, biology, hydrology, geology, and civil infrastructure to address challenges surrounding pollution control, water supply, wastewater treatment, flood mitigation, and ecosystem restoration. Central to environmental engineering is the principle of pollution prevention and control. Understanding pollutant sources, transport pathways, and transformation mechanisms in air, water, and soil allows the development of targeted interventions. Technologies such as air scrubbers, activated carbon filters, bioreactors, and constructed wetlands remove or neutralize contaminants ranging from particulate matter and volatile organics to heavy metals and pathogens. Chemical processes, including oxidation reduction, adsorption, and precipitation, underpin many treatment methods engineered to meet regulatory standards protecting public health and ecosystems. Water resources engineering focuses on the sustainable management of surface water and groundwater, critical for drinking, agriculture, industry, and ecosystem services. Hydrological modeling predicts stream flow, groundwater recharge, and watershed responses to natural and anthropogenic influences, integrating precipitation, evaporation, infiltration, and runoff components. Engineers design reservoirs, dams, canals, and levees, balancing water supply, flood control, and ecosystem preservation. Wastewater treatment encompasses multi-stage physical, chemical, and biological processes engineered to remove solids, organic matter, nutrients, and pathogens from domestic, industrial, and stormwater effluents. Primary treatments employ screening and sedimentation, removing coarse materials and suspended solids. Secondary treatments leverage aerobic and anaerobic biological processes, decomposing organic pollutants, converting them into biomass and harmless gases. Advanced tertiary treatments remove nutrients like nitrogen and phosphorus, preventing eutrophication in receiving waters. And disinfection using UV chlorination or ozone ensures microbial safety. Stormwater management integrates green infrastructure, bioswales, permeable pavements, rain gardens, mimicking natural hydrological processes, reducing runoff volume and peak flows. mitigating urban flooding and pollutant loads. Innovative retention and detention systems optimize stormwater quality and quantity, promoting groundwater recharge and enhancing urban resilience. Contaminated site remediation employs engineered methods, such as soil vapor extraction, bioremediation, chemical oxidation, and thermal desorption, removing hazardous substances, restoring ecosystem and human health. Risk assessment and monitoring underpin these interventions, ensuring effectiveness and preventing secondary impacts. Air quality engineering addresses the control of emissions from stationary and mobile sources using scrubbers, filters, catalytic converters, and alternative fuels. Dispersion modeling informs regulatory compliance and urban planning, minimizing population exposures. Emerging challenges include greenhouse gas mitigation, necessitating carbon capture, utilization, and sequestration technologies integrated within energy and industrial systems. Environmental impact assessments. EIA systematically evaluate potential effects of proposed projects, guiding design modifications and mitigation to minimize adverse outcomes on ecosystems, communities, and natural resources, ensuring sustainable development. Water treatment engineering treats raw water sources to produce potable water meeting health standards, employing coagulation, flocculation, filtration, and disinfection processes, tailored to source water quality and distribution system requirements. Infrastructure resilience incorporates design against natural hazards, floods, droughts, earthquakes, and climate change impacts through adaptive management frameworks. Embedding monitoring, early warning, and contingency planning, preserving service continuity and safety. Ecosystem restoration engineering integrates hydrological reconnection, reforestation, invasive species control, and habitat enhancement, revitalizing natural functions, supporting biodiversity, and carbon sequestration. Environmental data analytics and remote sensing technologies enable high-resolution spatial and temporal monitoring of pollutant dispersion, water quality, and land use changes, informing adaptive management and policy development. Sustainability considerations permeate environmental engineering, emphasizing life cycle impacts, resource efficiency, stakeholder inclusion, and regulatory alignment, ensuring that engineering interventions promote environmental justice and long-term viability. Global water scarcity challenges propel innovations in desalination, water reuse, leak detection, and demand management technologies, essential to urban and agricultural sustainability. Interdisciplinary synergy with social sciences ensures community engagement, behavioral change facilitation, and equitable access vital for successful environmental programs and infrastructure acceptance. In sum, environmental engineering and water resources management meld scientific understanding with practical technologies, crafting engineered solutions, essential to preserving the planet's life support systems, promoting human health, and enabling harmonious coexistence between development and nature. Robotics, artificial intelligence (AI), and automation technologies are reshaping the landscape of engineering, ushering in an era where machines not only execute repetitive tasks, but also learn, adapt, and collaborate with humans across diverse domains. This section provides an extensive examination of these transformative technologies, from foundational concepts and system architectures to cutting-edge applications and future trends driving innovation. At the foundation lies robotics, the interdisciplinary science combining mechanical design, electronics, control systems, and computing to build systems capable of sensing, decision-making, and manipulation of their environment. Robots range from fixed industrial arms performing high-precision manufacturing tasks to autonomous mobile robots navigating complex, unstructured environments like warehouses, hospitals, and disaster sites. Mechanical design focuses on kinematics, dynamics, and materials, ensuring dexterity, strength, and endurance balanced with weight, and energy constraints. Sensors imbue robots with the ability to perceive position, force, vision, and environmental conditions through encoders, acceleromotors, cameras, lidars, and tactile arrays, enabling real-time feedback essential for precise control. Control strategies in robotics span from open-loop models for predictable environments to sophisticated closed-loop adaptive systems, employing nonlinear control, reinforcement learning, and model predictive techniques. These algorithms enable trajectory planning, obstacle avoidance, manipulation dexterity, and cooperative multi-robot coordination. Advances in swarm robotics explore decentralized control, inspired by biological systems, enabling robust, scalable solutions to tasks like search and rescue and environmental monitoring. Artificial intelligence amplifies robotic capabilities by providing cognitive functions such as perception, reasoning, and decision-making. Machine learning models trained on vast data sets empower pattern recognition, natural language processing, and predictive analytics embedded within robotic systems for autonomy and human interaction. Deep learning architectures such as convolutional neural networks, CNNs, enable computer vision applications allowing robots to identify objects, navigate dynamic settings, and understand complex scenes. Reinforcement learning algorithms permit robots to learn optimal behaviors through trial and error, adapting to changing environments without explicit programming. Human-robot interaction. Dage RI designs interfaces and behaviors ensuring safe, intuitive collaboration with humans. Techniques include gesture recognition, voice commands, augmented reality overlays, and shared workspace dynamics, where robots comprehend human intent and constraints, fostering effective teamwork. Safety mechanisms incorporate physical compliance, force feedback, and emergency stop systems, guaranteeing operational security. Applications extend across manufacturing, where collaborative robots, cobots, enhance flexibility and ergonomics. Healthcare, through surgical robots performing minimally invasive procedures, and rehabilitation exoskeletons restoring mobility. Logistics and agriculture, through autonomous vehicles, streamlining supply chains, and precision farming, and exploration deploying robotic probes in space, underwater, and hazardous terrestrial environments. Robotics integrates with Internet of Things, IoT, and cyber-physical systems, creating interconnected ecosystems, facilitating real-time data exchange, remote operation, and swarm intelligence, enabling distributed sensing and coordinated actuation. Ethical, legal, and social implications receive growing attention as autonomous systems become pervasive. Issues around accountability, privacy, employment impacts, and decision transparency prompt the development of regulatory frameworks and design principles emphasizing human-centric, responsible innovation. Emerging frontiers include soft robotics, utilizing compliant, bio-inspired materials enabling gentle, adaptable manipulation, quantum computing enhancing AI processing power, and neuromorphic engineering, mimicking brain-like architectures, offering unprecedented efficiency and learning capacity. Sustainability considerations underpin design choices aiming to minimize resource consumption, enhance recyclability, and extend operational lifespans aligned with circular economy models. Simulation and digital twin technologies facilitate virtual prototyping, scenario testing, and predictive maintenance, reducing costs and accelerating deployment cycles. In essence, robotics and AI embody a confluence of multiple engineering disciplines, yielding systems capable of extraordinary adaptability, precision, and autonomy. Mastery over these technologies empowers engineers to create transformative tools, extending human capabilities, addressing complex challenges, and redefining the interface between man and machine. Biomedical engineering stands at the crossroads of life sciences and engineering, innovating technologies and systems that dramatically improve diagnostics, treatment, and quality of life. This multifaceted discipline integrates biology, mechanics, electronics, materials, and computation, creating devices and methods that fight disease, restore function, and advance human health like never before. A foundational innovation is medical imaging. Employing physics principles, X-rays, ultrasound, magnetic resonance, nuclear decay, to visualize the human body non-invasively. Techniques like computed tomography, CT, generate detailed 3D reconstructions, while magnetic resonance imaging, MRI, exploits nuclear magnetic resonance for exceptional soft tissue contrast. Positron emission tomography, PT, molecularly images metabolic activity, informing cancer, neurological, and cardiovascular diagnoses. Advances in image processing and artificial intelligence enable improved anomaly detection, segmentation, and personalized analytics, delivering enhanced diagnostic precision. Implantable biomedical devices have revolutionized patient care. Pacemakers restore normal heart rhythms through electrical stimulation. Cochlear implants partially restore hearing via direct nerve stimulation. Artificial joints and prosthetics leverage biomaterials and biomechanical engineering, restoring mobility. Emerging neural interfaces bridge brain-machine communication, enabling patients with paralysis to control external devices. Designing biocompatible materials that evade immune rejection while maintaining functionality is critical, involving polymers, ceramics, and bioactive coatings. Tissue engineering and regenerative medicine seek to repair or replace damaged tissues through scaffolds, stem cells, and growth factors. Biomimetic materials guide cell growth, differentiation, and vascularization, enabling engineered skin, cartilage, and even organoids. This field combines cell biology, material science, and bioreactor design, addressing challenges of mechanical strength, nutrient delivery, and integration with host tissue. Biomedical instrumentation encompasses sensors and analyzers measuring physiological signals, ECG, EEG, blood pressure, glucose levels, facilitating monitoring and early detection. Wearable health devices and implantable sensors provide continuous real-time data, enabling personalized medicine and preventive care, reshaping healthcare delivery paradigms. Drug delivery systems utilize engineering to improve precision, dosing, and targeting. Nanoparticles, liposomes, and polymers enable controlled release, crossing biological barriers, and minimizing side effects. Microfluidic devices and smart pumps tailor treatments, adapting dynamically to patient responses. Biomechanics analyzes the mechanical behavior of biological tissues and systems, informing injury prevention, rehabilitation protocols, and ergonomic designs. Understanding joint kinematics, muscle forces, and tissue elasticity enables development of assistive devices and performance optimization in sports medicine. Biomedical signal processing extracts meaningful patterns from noisy physiological data, supporting diagnosis, prognosis, and real-time intervention. Techniques include filtering, feature extraction, wavelet analysis, and machine learning, advancing telemedicine and ICU monitoring. Synthetic biology engineers, biological systems redesigning genetic circuits and metabolic pathways, creating therapeutic proteins, biosensors, and biofactories. Engineering cellular systems with modular, standardized parts enables targeted drug production and environmental remediation. Healthcare informatics blends data science, software engineering, and clinical knowledge managing, electronic health records, decision support systems, and population health analytics. Interoperability standards and privacy-preserving machine learning ensure effective, secure health data utilization, advancing research and care. Robotics in surgery and rehabilitation introduces precision instruments performing minimally invasive procedures, enhancing outcomes and recovery. Rehabilitation robotics provide consistent, adaptive therapy, facilitating neuroplasticity and motor function restoration. 3D printing and bioprinting revolutionize customized implants, prostheses, and scaffold fabrication, enabling patient-specific designs with rapid turnaround, reducing costs and improving integration. Medical optics and photonics enable laser therapy, optical coherence tomography, and fluorescence imaging, advancing cancer treatment, ophthalmology, and tissue characterization. Nanomedicine exploits nanoscale materials for diagnostics and therapeutics, delivering unprecedented specificity and efficacy with minimized toxicity. The integration of systems biology provides holistic views combining multi-omics data to understand disease mechanisms, guiding precision engineering of interventions. Emerging frontiers include brain-computer interfaces, gene editing technologies, wearable bioelectronics, and AI-driven drug discovery, converging engineering and life sciences toward transformative healthcare futures. In essence, biomedical engineering encapsulates a synergy of disciplines committed to unraveling biological complexity and translating it into innovative solutions, profoundly enhancing human health, longevity, and well-being. Data science and machine learning (ML) have emerged as transformative forces across engineering fields, blending statistical rigor, computing power, and algorithmic innovation to unlock insights from complex data and automate decision-making. These disciplines enable predictive modeling, optimization, anomaly detection, and control applications essential for modern engineering challenges, involving vast dynamic datasets and uncertain environments. At the heart of this revolution is the concept of data-driven modeling, where vast historical and real-time data replace or augment traditional physics-based models. Engineers use regression techniques, clustering algorithms, principal component analysis (PCA), and dimensionality reduction techniques to uncover underlying patterns, correlations, and system behaviors previously hidden. This approach excels in complex systems where explicit mathematical formulations are infeasible or costly, such as turbulence prediction, materials property estimation, or predictive maintenance. Machine learning algorithms range from supervised learning, training models on labeled datasets for tasks like classification, regression, and forecasting, to unsupervised learning, discovering intrinsic data structures without explicit labels, useful in anomaly detection or feature extraction. Reinforcement learning imparts decision-making capabilities through trial and error interactions, optimizing policies for control and robotics applications. Deep learning, a subset of machine learning, employs layered artificial neural networks, mimicking brain architectures, processing unstructured data such as images, speech, and natural language. Convolutional neural networks, CNNs, excel in visual pattern recognition, enabling defect detection in manufacturing, medical image segmentation, and autonomous vehicle perception. Recurrent neural networks, RNNs, process sequential data, facilitating predictive maintenance, speech synthesis, and time series forecasting. Feature engineering, transforming raw data into informative inputs, remains crucial for model performance. Techniques include normalization and coding categorical variables, creating interaction terms, and detecting nonlinearities. Automated feature extraction via deep learning architectures reduces reliance on manual input design, accelerating deployment. Model evaluation employs metrics such as accuracy, precision, recall, mean squared error, and area under ROC curves, ensuring robust, unbiased performance assessments. Cross-validation, regularization, dropout, and early stopping mitigate overfitting, balancing generalization and complexity. Optimization algorithms, gradient descent variants, genetic algorithms, particle swarm optimization, drive model training, and engineering design optimizations, solving constrained, multi-objective problems, balancing trade-offs, essential in product development, structural optimization, and energy management. Explainable AI addresses the black box nature of many ML models, enhancing interpretability, crucial for safety-critical engineering domains. Techniques like SHAP values, LIME, and attention mechanisms reveal feature importance and model rationale, supporting trust and regulatory compliance. Big data infrastructures, cloud computing, distributed databases, parallel processing enable scalable data storage, processing, and analysis, managing the volume, velocity, and variety of engineering datasets from sensors, simulations, social media, and enterprise systems. Stream processing frameworks facilitate real-time analytics, enabling predictive maintenance, adaptive control, and anomaly detection in manufacturing and infrastructure. Industrial Internet of Things. 2IoT integrates sensor networks, edge computing, and ML models, fostering intelligent manufacturing, smart grids, and autonomous systems. Digital twins, virtual replicas of physical systems augmented with real-time data and ML models, permit predictive analytics, scenario testing, and system optimization, driving operational excellence and innovation. Uncertainty, quantification methods, incorporating Bayesian inference and probabilistic modeling, enable engineers to assess and mitigate risks, enhancing reliability and safety in design and decision-making. Collaborative AI-human systems blend machine precision and human creativity, effectively handling complex, ambiguous engineering problems. Emerging paradigms include federated learning, preserving data, privacy across distributed sources, quantum machine learning promising exponential speedups, and neuromorphic computing, enabling energy-efficient AI, mimicking brain processes. Ethical considerations emphasize data privacy, bias mitigation, transparency, and equitable technology deployment, addressing societal impacts of algorithmic automation. Education and workforce development adapt integrating data science and AI competencies, ensuring engineers harness these tools responsibly and innovatively. Data science and machine learning constitute a paradigm shift, infusing engineering with new analytical, predictive, and adaptive capabilities, unlocking tremendous opportunities to design smarter, safer, more efficient systems, addressing complex real-world problems. Safety engineering and monitoring embody the critical guardianship of engineered systems, ensuring protection of human life, assets, and the environment amidst increasing complexity and scale. This multifaceted discipline integrates hazard identification, risk assessment, system design, real-time monitoring, and incident response, establishing resilient systems capable of anticipating, preventing, and mitigating failures and accidents. Foundational is the concept of hazard analysis, systematically identifying potential causes of harm, mechanical failures, human errors, environmental events across system components and interfaces. Techniques such as fault tree analysis, FTA, failure mode and effects analysis, FMEA, and hazard and operability study, HAF, dissect system functions, uncovering vulnerabilities, guiding design improvements, and preventive controls. Risk assessment quantifies hazard probability and consequence, enabling prioritization of mitigation efforts. Probabilistic risk assessment, PRA, incorporates uncertainties, cascading failure scenarios, and human factors, delivering comprehensive safety profiles, supporting decision-making and regulatory compliance. Incorporating safety by design, engineers embed protective features into system architecture, redundancy, diversity, fail-safe mechanisms, safety interlocks, minimizing likelihood and impact of failures. The use of inherently safe materials, ergonomic interfaces, and error-tolerant processes reduces human error contributions. Real-time monitoring systems utilize sensor networks measuring temperature, pressure, vibration, chemical concentrations, structural strain, and more. Data fusion and analytics detect early warning signs, enabling condition-based maintenance, preventing catastrophic failures. Supervisory control and data acquisition, SCADA, and programmable logic controllers, PLCs, implement automated safety protocols, performing emergency shutdowns or reconfigurations, ensuring system integrity. Human reliability engineering studies, interactions between operators and systems, designing user-friendly controls, alarms and interfaces, minimizing human error, and enhancing situational awareness. Training programs employing simulators and virtual reality immerse operators in realistic scenarios, elevating preparedness. Organizations cultivate safety culture, embedding safety values into behavioral norms supported by reporting systems, encouraging near-miss disclosures, fostering continuous improvement without punitive fear. Regulatory frameworks and standards such as ISO 450-501 and industry-specific guidelines mandate rigorous safety management systems encompassing planning. Emergency preparedness integrates scenario planning, response coordination, evacuation protocols, and recovery strategies, minimizing impacts of incidents, preserving life and functionality. Cybersecurity complements physical safety, safeguarding control systems against malicious attacks, ensuring operational safety in increasingly connected infrastructures. Advances in predictive analytics and machine learning enable proactive risk identification and adaptive safety controls, responding dynamically to evolving conditions. Safety engineering extends beyond prevention to include resilience, ensuring systems maintain critical functions or recover swiftly post-disturbance, minimizing disruption. Ethical considerations ensure engineering decisions prioritize human welfare and environmental stewardship, reflecting social responsibility intrinsic to sustainable engineering. In sum, safety engineering and monitoring form the indispensable guardians, assuring that the marvels of engineering serve humanity reliably, safely, and responsibly, preserving trust in the technologies shaping our world.